Let's say we're trying to evaluate the limit of 5x cubed minus 2x squared plus 3x minus 2 at 2. It's a sum, and we know that the limit of a sum is the sum of the limits. And on the other hand, each one of the terms is a constant multiple of a power of x, and we know that when we have a constant multiple, limit of a constant multiple, we can pull out the constant. And on the other hand, we know that the limit of a power of x at a is a to that power, and that the limit of a constant is that constant, and therefore this is what we obtain for the limit. Now you see that this is simply what we would obtain by plugging x equal to in the function. Of course, the argument we gave here would apply to any polynomial, because a polynomial is simply a sum of constant multiples of integer powers of the variable. So that means that if f of x is a polynomial function, then to obtain the limit of f of x at a, you just plug in x equal a in the function f. You just evaluate the function. Since a polynomial is defined on the entire real line, that means in particular that a polynomial has a limit at every a, and this limit is easy to obtain. You just plug in the value. What if we have a rational function instead? By a rational function, I mean a quotient of two polynomials. As long as the limit of the bottom is not 0, I can say that the limit of a quotient is the quotient of the limits. In this case, there's no problem because the limit of x plus 9 is a polynomial, so to get that limit I can plug just x equal 1 inside that function. I get 10, which is not 0. So I get the quotient of the limits. Now, at the top I have the limit of a polynomial, at the bottom I have the limit of a polynomial. To obtain these limits, I just need to plug in x equal 1. In this case, I get 0 at the top, 10 at the bottom, so that's 0 over 10 equals 0. In other words, as long as x equal a is not a 0 of the bottom, in other words, as long as x equal a is in the domain of the rational function, I can do exactly the same thing. Obtain the limit by plugging x equal a inside the function. Now what if a is a 0 of the bottom? In other words, x equal a is not in the domain of the rational function, like in this example. Right? If you plug x equal 1, then you obtain 0 at the bottom. You divide by 0, then we have a problem. Let's look at this example. X squared plus 3 over x minus 1 is graphed here. And you see that when we get close to x equal 1, well, the values of the function grow without bounds and the limit does not exist. In general, if we have a situation where we have two expressions and we divide one by the other, the expression at the top is non-zero at x equal a, but the expression at the bottom is equal to 0 at x equal a, but then the top gets close to non-zero value and the bottom gets closer and closer to 0. So you have a non-zero value that you divide by values that are smaller and smaller, which is the same as multiplying by reciprocals, which are going to be bigger and bigger. And in that case, the values of the function, of the quotient, are going to grow without bounds, and therefore the limit will not exist. Let's take a look now at the case where both top and bottom are approaching 0 as x is approaching a. In other words, if I plug x equal a, at the top I get 0, at the bottom I get 0. This is called an undetermined form of the type 0 over 0. Why undetermined? Because we cannot just decide from this what the limit is. Let's look at some very basic example to convince ourselves that we cannot decide. For instance, if I look at the limit when x is approaching 0 of x over x. Of course, the top and the bottom are both x, and therefore both top and bottom approach 0 as x approaches 0. But x over x is equal to the constant function 1 everywhere except at x equals 0, because x over x is not defined for x equals 0, but the constant function 1 is. Nevertheless, they have the same limit at x equals 0 because the limit doesn't depend on the value at 0, but only on the values near 0. So this is the limit of the constant function 1, and therefore this is 1. On the other hand, I could take another example of something going to 0 over something else going to 0. For instance, 17x over x. Both top and bottom go to 0 when x goes to 0. But 17x over x coincides with a constant function 17 everywhere except at x equals 0. Therefore, they have the same limit at x equals 0, and this limit is 17. A third example, let's say I look at x squared over x. Of course, both top and bottom go to 0, but x squared over x coincides with a function x everywhere except at 0, and the limit of the function x at 0 is of course 0. On the other hand, if it was x over x squared, both top and bottom go to 0, but this function coincides everywhere but at 0 with the function 1 over x. And 1 over x, by the argument we gave before, doesn't have a limit at 0 because the top is a constant and the bottom approaches 0. So we have the previous case of something non-zero over 0. So you see that we can really have all sorts of situations. We got examples where the limit is 1, 17, 0, or does not exist. So we cannot predict in advance, just from the fact that we have 0 over 0, what the limit is going to be. Now we're going to see what we can do to try to lift the indetermination. Let's start with the case of a rational function. We have a quotient of two polynomials, and they are both 0 at x equal 2. Indeed, if you plug x equal 2 at the top, you get x squared is 4 times 2, 8, plus 2, 10, minus 10, 0. At the bottom, you plug x equal 2, you get 4 plus 2, 6, minus 6, 0. The key thing to have in mind for this type of exercises, quotient of two polynomials, and you have an undetermined form of the type 0 over 0, is this general result. If you have a polynomial, it is 0 at a certain value if and only if x minus a can be factored out of that polynomial. So what does that mean? That means that if both top and bottom are 0 at x equal 2, x minus 2 should be a factor in each one of these two polynomials. So what do? Well, we simply factor the top and factor the bottom. And that's not hard to do because we know in advance that x minus 2 is a factor in each one of them. So to factor in particular, so we get a common factor x minus 2. To factor this, let's say for the top, you know that you need to have 2x squared starting with x on the factor x minus 2, which we know is one of the two factors. So to get the other factor, you know that you're going to need to have 2x in the second factor in order to obtain 2x squared. On the other hand, if you look at the constant term in the top polynomial, it's negative 10, and we're going to obtain this constant term by multiplying the constant term of the two factors. The constant term in the factor x minus 2 is negative 2, so that means we need plus 5 in the second factor. Now that we have this common factor x minus 2, we can cancel it out. When we do this cancellation, of course, we assume that x minus 2 is not 0. We're just dividing top and bottom by x minus 2. And to do that, we need to assume that x minus 2 is not 0. In other words, that x is not 2. But we know that we don't change the limit by doing that because the limit does not depend on the value at x equal 2. Therefore, we get something that has the same limit as 2x plus 5 over x plus 3. So we had the limit of of the quotient of two polynomials, and this limit was undetermined because both top and bottom were 0 at 2. After this factorization process, we see that the limit is the same as the limit of another rational function, but for which now x equal 2 is in the domain, so to obtain the limit we can just plug x equal 2 and we obtain 9/5. You see that here the key property to solve this type of problems is to remember that for a polynomial, taking the value 0 at a means x minus a is a factor in the polynomial. Let's look at a different kind of example now. The limit, as t is approaching -2, of square root of 11 plus t minus 3, all this divided by t squared plus t minus 2. First thing we try to do is plug t equal -2 in this expression and see what we get. At -2, root of 11 plus t is root of 9, in other words 3, so I get 0 at the top. T squared is 4, so I get 4 plus minus 2, so that's 2 minus 2, 0, so I get 0 at the bottom again. So it is another example where I have an undetermined form of the type 0 over 0. However, this time I cannot simply factor because the top is no longer a polynomial function. So the fact that it is 0 at -2 cannot be interpreted in terms of what can be factored out of it. So we need to do something else. Here there is a standard algebra trick to get rid of the radical. Of course, if we didn't have that radical, we would be in better shape and we would be able to factor. So how do we get rid of the radical? It is based on the fact that a difference of two squares can be factored as the product of the difference and the sum. Now, if we look at it the other way, if you have something of the form either a minus b or a plus b, if you multiply by the other one, you get a difference of squares. If a and b contain radicals, the difference of squares will not. So if this is my a minus b, in other words a is root of 11 plus t and b is 3, then I would like to multiply this by a plus b in order to get rid of the radicals. But since I have a fraction, if I want to keep the value of the fraction intact, if I multiply the top by a plus b, I need to multiply the bottom as well by a plus b. So what is a plus b here? It is what we will call the conjugate of root of 11 plus t minus 3, and that is root of 11 plus t plus 3. If I multiply top and bottom by this quantity, I didn't change anything. I just rewrote the same fraction differently. But now at the top I have something of the form a minus b, a plus b, and this is the difference of the squares. So I get the square of root of 11 plus t, and this is simply 11 plus t, minus b squared, in other words minus 3 squared. At the bottom I have my polynomial t squared plus t minus 2 multiplied by this conjugate quantity that we use. Now this polynomial was 0 at -2, and that we know that means that t plus 2 can be factored out of this polynomial. So we're going to factor this polynomial as t plus 2t minus 1. Note that at the top we have 11 plus t minus 9. 11 minus 9 is 2, therefore the top simplifies as t plus 2. And now we have a common factor t plus 2 that we can cancel because if we cancel it, we divide top and bottom by t plus 2, and we can do that as long as t is different from -2. But that's okay because the value at -2 doesn't affect the limit at -2. So we get the same limit as a function 1 over t minus 1 multiplied by root of 11 plus t plus 3. For this new function, I can plug t equal -2 and get something that makes perfect sense. I get -3 multiplied by 6 at the bottom, in other words -18, and therefore the limit is negative 1 over 18.